Hey, this is my circuits lab. So starting off with the purpose was to predict the behavior of circuits with series and parallel resistors and explore the behavior of resistors and capacitors and measure the conventional currents and potential differences. Fundamental principles in play include the node rule stating that current flowing into a node must equal the current flowing out of a node. Loop rule basically saying that the sum of all electrical potential differences around a loop is zero, and Ohm's law, and that the current through a conductor between 2 points is directly proportional to the voltage across the points. And then capacitance, which can be represented as the charge divided by the voltage. So our overview, we used an online simulation to construct and test a simple series and then RC parallel configured circuit each. Our results found that the Kirchhoff's laws or node and loop rule are true as validated by our experimental results and predicted values. And then series circuit current I was found to be 0.204 amps, and then our time constant 6.897 seconds. And then our main ideas again is going into the node rule, which is basically derived by Kirchhoff's current law, and based on the conservation of charge, so that current in is equal to the current out. The loop rule derived from Kirchhoff's voltage law, essentially the conservation of energy, so that change in potential or the delta V is going to be equal to zero in summation for the whole circuit. And then our Ohm's law that basically allows us to represents our elements in different ways. So in terms of the conservation of charge and energy in the series, we first found our system to be a circuit and surrounding to be everything else for this image that was given. So we basically took our total resistance from these two resistors, found that to be 147 ohms, and then plugged that into our Ohm's law formula, and derived our total current to be 0.0204 amps, and the same between both of those because the current is conserved throughout the circuit. And then we basically took the image given and recreated the circle in an online simulator and found our ammeters to essentially match what we previously calculated. And then reversing an ammeter would have no real difference as seen here. Replacing an ammeter with a voltmeter, if it was replaced, the voltmeter's resistance being notably high would cause the circuit to essentially function like an open circuit, causing the ammeter to read a current of zero. The voltmeter would also then read a voltage of -3 directly from the total of the battery flowing through the circuits, and then no other parts of the circuit will be contributing to the potential difference. Here we apply our loop rule for our circuit components, using our previously calculated current for the loop right here, as you see. Things that contribute to the potential difference include the resistors and batteries, as we see, and then once again applying our Ohm's law, we are able to calculate each potential difference throughout the circuit being plus 3 volts from the batteries, negative 0.96 from the 46 ohm resistor, and negative 2.04 from the 100 ohm resistor. Now we finished this diagram, as you can see here, visualizing the relative potential versus position around the circuit. So through the conservation of energy, we know that the voltage or potential difference in total should sum to zero. We also know that the gain voltage from the batteries, as we see here, and then drop from resistors, particularly harder or a steeper drop from the higher ohm resistor. Even if we attach a voltmeter, the ammeter's output should not change, as the voltmeter has a high resistance that doesn't allow current to flow through it. Placing an ammeter parallel to the 100 meter ohm resistor, we saw the negligible resistance of the ammeter in this ideal system, and the current and or electrons take the path of least resistance and flow through that instead of the resistor. So this brings the total circuit resistance to 47 ohms, and with this we can now plug in our values into our ohms equation and saw that the output shows basically what the ammeters are over here. Next we took Ohm's law, reorganizing it to solve for resistance, as you see here, V over I, and then plugged in um, what's it called? Our previously found potential differences and found our resistance to be 48 ohms for CD here, EF to be 102, and the rest of it to be zero. So basically closely aligning with our predicted values in comparison. And then getting into our resistor capacitance circuit, we saw that charging and discharging for both the 10 and 20 ohm resisting light bulbs took 7.98 seconds and 7.7 seconds and 16.69 seconds and 15.32 seconds respectively. And then here we examined the time dependence voltage or dependent voltage across a discharging capacitor in an RC circuit, looking to validate our predicted time constant here, using this linear function that we were basically able to map out and we're told, and then found that our real value of our time constant also matched that at 6.897 seconds. In terms of if we had an actual ammeter, the ideal ammeter had like negligible resistance, while an actual ammeter would have some resistance. So this would increase the total resistance and decrease the current due to the relationship of Ohm's law. And then if we used a real battery to charge a real capacitor with no resistance in the circuit, we would not have that slowing of current. And so this would allow the capacitor to charge instantly. In an actual system, that similar to what this was asking up here, all elements of the circuit, like batteries, would have intrinsic resistance, and so the instantaneous charge of the capacitor would not occur. And then our simulator didn't really allow us to have much error in terms of this lab, but human error in terms of measuring the discharging capacitor voltage for that distance dependence is what could be in play.